So a class A address So in a class A IP address, the first 8 bits or the first octet is designated for the network addresses. Normally, we usually have two sets of addresses. There is what we call the network addresses, and there is what we call the host addresses. So in most of the places, you will need to have more host addresses because one network can have many host addresses or node addresses. But now, the other three octets are going to contain the host addresses. So the first bit, which is always a 0, is used to indicate the address as class A address, and the remaining 7 bits are used to designate the network. Then, in the class A address, there are 128 class A network addresses. But because the addresses with all zeros aren't used, address 127 is a special purpose address, and class 126 class A address network addresses are available. Then we come to class A addresses, whereby you will find that you can have 16,777,214 host addresses. Rather than remembering this number exactly, you can use the following formula, whereby you are talking about n being able to represent the number of bits in the host portion. So raised to the power of n minus 2 is the number of available hosts. Again, in class A addresses, that is why we are talking about 24. So it is 2 raised to 24 minus 2. And here you can use that formula to determine the number of networks in an address class. And so when we are talking about class A addresses, we are saying that it is going to use 7 bits to determine the network. So it is going to be 2 raised to power 7 minus 2, which can be 126. And so we are saying that we are going to have 126 class A networks. When it comes to class B addresses, then the first 16 bits are going to be used for the network addresses, meaning that the first 2 octets are going to be used for network, the last 2 octets are going to be used for the host addresses. And so the first 2 bit, which is always 10, designate the address as class B address, and then the 14 bits that are used to designate the network. This leaves 16 bits to designate the hosts. This is how it looks like. So you're going to have the formula of 14, 2 raised to power 14, and you can always have 16,382 networks, and each network can also have 65,534 hosts using that same formula. Then we have class C addresses, whereby it uses the first 24 bits, the first 3 octets for the network addresses, and only the last octet for host addresses. And so the first 3 bits of all class C addresses are set to 110, leaving 21 bits for the network addresses, which means that you can always have over 2 million class C networks, but only 254 hosts per network. And so this is how it is going to look like. So class A, you're going to have the 0 up to 127, because we have said 127 is a special purpose address. And so bits in the network is going to be 7 bits in the network ID, and number of networks is going to be 126. The host ID is going to be 24, and then you're going to have a total of 16 million hosts on the network. Then class B, and this is where now it needs to make sense. Any small network, very few networks are going to have this number of hosts, right? Just a single network. That is why you need to have many networks, because Small and private networks are usually very small, having a given number of hosts. So that is why you need to have a few hosts, which is like 254, and then you can have many networks. So class C is going to have an advantage because you can have many small networks which are able to be connected to create the internet, and they have many hosts, or many hosts are going to be found in many networks. Now, few addresses have been set aside for special purposes, beginning with this one, which we are calling 127, is what we normally talk of a look back address or a test address. So all the zeros are going to be the default Cisco root addresses. Then host addresses, the ones we have talked about, they are going to be zeros. And then the ones are used for broadcast on the local network. That is why when we'll be talking about the subnet masks, we'll be talking about 255, 255 as the host addresses or the broadcast addresses. Then we have the network addresses, which will start from 192, then all the way to 255, and then 127 is now used for look back testing or testing the connectivity of that particular device you are using. So within each address class, there is a set of addresses that are set aside use in the local networks, as well as sitting behind the firewall, or what we call network address translation. And these are the addresses to which devices can connect, or networks can be connected to the internet. So in class A, we have the 10.255.255.255. In class B, we have 172.16 up to 172.31.255.255.255. Then class C, it is 192.168.0.0 up to 182.168.255.255. Then we come to subnetting. And so, like we have said, an IP address is going to have two parts. So there is the one for network and the other one for host identification. And like we have said, when you look, if it is class A, you look at the first octet. If it is class B, you look at the first two octets. And if it is class C, you're going to look at the first three octets to know which network address it is. And then the last octet is for identifying the particular host on the network. So the network and host portions of the address are normally extracted separately. And if you know the address class, then it is easy to separate the two portions. And so, why do we need to have the subnet? And with the rapid growth of the internet and the demand for new addresses increasing, the standard address structure is expanded by borrowing bits from the host portion to allow for more networks. So, under this addressing scheme, which we call subnetting, then you separate the network and host addresses by requiring a special process which we call subnet masking. So the subnet masking is the process that is developed to identify and extract the network part of the addresses. And a subnet mask is going to contain a binary bit pattern of ones and zeros, and is going to be applied to an address to determine whether the address is on the local network or not. If it is not, the process of routing it to an outside network is going to begin. So that is the basic concept in subnetting. And when we are talking about it as a function, it is normally used to determine whether an IP address exists on the local network or whether it must be routed outside the local network. It is applied to a message's destination address to extract the network address, and then if the extracted network address matches the local network ID, then the destination is located on the local network. Now that is a bit complicated, but when we are looking at them, just to basically understand from the top, is that an IP address is going to be the logical numerical address that is assigned to maybe a printer, a computer, a switch, a router, or any other device that is in the TCP/IP network. Then a subnet, we are saying that, is supposed to identify or to separate the network with the hosts. So an organization's network can either be in one floor of a building or one building or in a particular geographical location. So that is where you create a network, and that network most of the time will be identified using maybe a particular switch address or a particular router address, because it is the routers which are supposed to create a network or a particular network segment. So a particular network segment will have maybe 10 computers, and these 10 computers are connected to a switch. Then that switch is connected to a router to create that segment. And so a subnet mask is going to be a 32-bit number that is used to differentiate the network component of an IP address by dividing the IP address into network address and a host address. So that is where the aspect of subnetting is coming in and how to extract it. So if they are not going to match the host and the network address, then the message must be routed outside the local network. So the process used to apply the subnet mask is going to involve Boolean algebra to filter out non-matching bits to identify the network address. So this is how it is. It is a process that applies binary logic to yield binary results, and it works with subnet masks. So you need only 4 basic principles of the Boolean algebra, whereby we say a 1 and a 1 is going to be a 1, a 1 and a 0 is a 0, a 1 and a 0, a 0 and a 1 is a 0, and a 0 and a 0 is a 0. So the only way you can get a result of 1 is to combine 1 and 1. Everything else is going to result to a 0. That is what we call ANDing. When you learn about computer logic, you understand the logic gates where we talk of AND gates, NOT gates, and NAND gates. So ANDing is that process of combining these binary digits so that you can end up with either a 1 or a 0. So the default standard subnet masks for class A, B, and C is like this, whereby the first octet is the network. In a class A, the first octet is the network address, and that is the subnet mask, whereby you look at the first octet is 255 and the other one is 000. In class B is the first two octets, which is 255.255, then 00 or any other value that is assigned. Then class C, the first three octets is 255, 255, 255, and then the other ones. So the default subnet masks are like that. So how do we now start applying either to class A or to class B or to class C addresses? So the subnet mask is like a filter that is applied to a message's destination IP address, and the objective is to determine if the local network is the destination network. This is how we can use. So if an IP address is 206.175.162.21, so this by default, we know it is class C address. Why? Because 206 is in the range of 192 up to 223. So that one is a class C address. So once we know that, then the binary equivalent will look like this. And then we will move on now to know that the default standard class or the subnet mask is going to be 255, 255, 255.0. And the binary equivalent is going to be like that. So how do we do the separation? When these two binary numbers So when these two binary numbers are combined through the process of ANDing, which we have talked about, that is the IP address and the subnet mask, then the network ID of the destination is the result, whereby we are saying is 206.175.162.121, and then you AND it to 255.255.255.0, which looks this way. So when these ones are ANDed, whereby we said that if it is 1 and a 0, it's going to be a 0, 0 and 0 is 0, 1 and 0 is 0. That is why everything here comes to 0, and then followed by this other one. It is ANDed that way. Anything you are combining or you are ANDing is 0 and 1 is going to be a 0. Only where there is 1 and 1, you're going to have a 1. So this is the value that we are getting, and that should give us the IP address was this one, then the subnet mask was this one, so that it can give us a network address of 206.175.162.0. So the network address is that one which has become this. It is generated out of this ANDing process which we have talked about. So the IP address of the network is the same as the local network, and it means that the message is for a node in the local network. It doesn't need to move outside that particular local area network. So if an IP address is verified using ping, trace, and telnet, things we shall try, then it is important to know that ping is used to verify an IP address connections to the network layer, and that telnet is used to verify IP addresses connections to the application layer that we shall try out practically. So the reason why you need to verify IP addresses is to ensure that the various parts of a network can properly communicate with each other, or they can communicate with other parts of the network. And if you can telnet, that is terminal emulation, into a router for a remote connection in the network, then you can verify the interface and route and are up to the standard. So Telnet is going to operate at the application layer. When it is functioning, it is safe to assume that all the lower layers are functioning. When you are using ping, it is going to operate at the network layer. So it will send out an ICMP message to verify both the logical and physical addresses or the physical connections, because physical connections are going to operate in the first and second layer. That is the physical and the data link layer, and then the network layer is the one where IP addresses are operating. So that is how you verify them. So the ping command, which is issued from a Cisco router, responds to a number of single character responses. When there is an exclamation mark, it means that it has been successful. If it is a period, then there is a timeout. If it is a U, then the destination is unreachable. If it is a vertical bar, the process is interrupted. A question mark, it is a known packet type. A C is congestion which has been experienced, and then an ampersand means that the time to live has been exceeded or it has timed out. So how do you verify the trace route or tracing a route? The trace route is supposed to give you the route that is taken from a packet will take from source to the destination, and also show you the number of hops or the number of nodes it will go through to get to that particular destination. That is what a trace route does. So once you trace the destination IP address, the trace route command will show you the route that has been taken and to get to the particular the destination. And it is going to display the round trip time for each packet sent to each upstream router, and it has only two results. Either it can tell you time has been exceeded, and destination is unreachable, and it is used to determine where breakdown in a route may be occurring. Those ones we will do them practically. So if you want to trace or a network has four routers, A, B, C, D, and a trace command is issued on router A to trace the route from itself to router D. A timing response comes back from the router B, but the next message indicates that the router C is unreachable. Then you can be fairly certain that the problem lies somewhere on route between router B and router C. For example, if I can be able to show this one practically, when you are doing it, you needed to do it, you get into the command prompt, and maybe I can share this one. And for instance, I would like to trace a route. That is how trace route command is given in Windows, that is traceat, and maybe I say that is google.com. I press. So one of the things that is going to happen is that there is going to be a conversion of google.com, which is the domain name, to the particular IP address, which is 172.217.170.174. So one thing we know by default is that the 172 is going to lie in the class 2 IP address. So this is a class B IP address. Then we are using the maximum number of hops is 30 hops, meaning that once you reach 30 hops, then there is going to be a timeout. But it has only taken 9 hops or 8 hops to get to the destination address, whereby we started with maybe this machine IP, the network IP address is 172.16.1.1. Then it went to 187, which is a class 3, so a class C. So that means that it is a network within the university as well. So this one is for the local network or the local network address. Then this one is the network address for our router, and then we connect to the KenNet service provider, maybe within the Machakos region, and then that is why it is spumacha.kennet, and then it goes to the CCOM KenNet network, maybe somewhere in Nairobi or Mombasa, and then from there it moves to the next router, another router in between, another one, until you get to the destination address, and that is how you can be able to trace a route from a particular network or from a particular node source and a particular destination. So that is how trace route works. Then let us continue. When you are verifying the trace route, you can do a ping. And when you do a trace route, if there is an asterisk, it means that there is a timeout. If it is an exclamation mark with a H, it means that the router received the packet, but it did not forward it, meaning that there is an issue of access list, something we will cover as we continue with the CCNA classes. If there is an N, it means that the network is unreachable. If it is a P, the protocol is unreachable. If it is a U, the port is unreachable. And then we have the classless interdomain routing. When we are talking about classless interdomain routing, it means that the IP version 4 network addresses have been exhausted, and then you need to increase the size of the internet's routing tables. And so, how do you do that? It does that by using the CIDR, the classless interdomain routing, something we will cover in our next class. So features of CIDR is that it eliminates the class 4 addressing, It is enhanced for router aggregation. It is good for supernetting and classless addressing. Thank you.